In this video, we're going to talk about topic 4.3, or how we represent reactions. So the statement, the objective for this is to represent a given chemical reaction or physical process with a consistent particulate model. So we're going to look at how we model these. Now, the first thing to consider when we go to model these is the law of conservation of mass. So when we go to draw these particle diagrams, we always need to be keeping the law of conservation of mass in mind while we're doing this. So reminder, law of conservation of mass says that matter cannot be created or destroyed. Okay, so we can't have more particles in our products than we started with in our reactants. We can't have more particles in our reactants than we end with in our products, because we can't just randomly create particles. We can't just make them vanish and go away. We use coefficients to balance reactions. So we've been doing this since we started talking about chemical reaction equations. So the coefficients show us those ratios so that we end up with the same number of particles before and after. When we go to draw these, we're going to draw these as particle diagrams. So these are the same types of particle diagrams you've drawn in previous classes. So oftentimes we use circles with maybe sometimes they're shaded in, or they have lines through them, or they're just open circles to show different types of elements, different atoms. And when we draw these, we have to represent the correct ratios. So again, based on the coefficients, you can't have more particles after than you started with. You can't have more before than you end with. So you have to have balanced on both sides. You also have to show what's happening. You can't just draw random particles and call it good. So if they're connected, if it's a solid, you have to show them connected to each other as a solid. So if we're going to go back to our previous reaction, if you have a silver and a chloride ion and they're stuck together, they need to be stuck together. Okay, and then when we're talking about ionic aqueous solutions, oftentimes you'll be asked to show how they're going to be attracted to the different parts of the water. Okay, so if we remember our water molecule, our water has an oxygen and two hydrogens. Our hydrogens have partial positive charges. Our oxygen has a partial negative charge. So the oxygen part of our water molecule is going to attract positive things. So a positive ion would be attracted to the negative side of the water. Sometimes you'll see that with a dashed line between the two things. So in our previous example, we had potassium chloride was soluble in water. So the potassium's the positive. So we'd have the potassium drawn up here with maybe a dashed line showing how it's attracted to the negative part of the water. And then the chloride ion, which is a negative charge, would be attracted to the hydrogen, which is the positive part of the water. So you could do it the same way. So you draw a circle with a Cl minus in it and maybe a dashed line connecting over to the hydrogen. Sometimes you'll be asked to draw that. Sometimes you'll be given the drawing. And so you're looking for all of those pieces. Are the solids represented correctly? If they're in aqueous solution, are they attracted to the correct parts of the water molecule? And again, all of this done with law of conservation of mass in mind. You can't have more particles at the beginning than at the end, because we can't just randomly vanish atoms. And you can't have more at the end than you started with, because you can't just randomly create atoms either. So all of these pieces together we can use to draw particle diagrams to represent different types of chemical reactions.